Okay, so welcome back. Grace, this is Beachside Bunny. I'll type that into chat. Anyway, welcome back. Hope you all had a good weekend. My tooth is feeling a good bit better, so I'm in better mood today, which means there's Mountain Dew to be drank. So last time I'd kind of finished with. Well, let me just bring back the sheet. So, tangent, normal vectors, the curves. This is kind of the most important thing that we want to talk about when we're talking about curves in space. This is us taking the things that we did in Calc 1 and Calc 2, specifically Calc 1, when you wanted to talk about the graph of a function. Typically, the graph of a function that we discussed in Calc 1 was a curve. And we were very interested in things like finding the tangent vector to the curve at some point. Of course, it wasn't framed like that. It was finding the slope of the line tangent to the graph of a curve at some point. But of course, if you know the slope of that line, you already know a point on the line, so then you know the line itself. And of course, a line we could view as giving us information about the tangent vector at that point. So if I draw, if I go back to Calc 1 world, and I think, okay, so in Calc 1, we were interested in questions like find tangent line, right? This is literally the main thing that Calc 1 was concerned with, and applications of this fact. So find tangent line to the graph of this function at this point. So this is a curve in the plane. Right, and so if I draw in a sketch of the tangent line, of course you know how to find this. If I draw in sketch of tangent line to curve at point, of course I could find this line just by, I know the point on the curve and I find the slope of it by computing the derivative of the function. This line, of course, determines a bunch of tangent vectors, right? So for instance, if I pick this one, that's a tangent vector to this curve at that point. So is this one. We'll talk about that a little bit later. So is this one. Right? So is this one. That's also a tangent vector. All of those are tangent vectors to this curve at that point, right? Meaning vectors that are tangent in the same way that a tangent line is tangent to the graph of a curve. So how do I know which is the best one to pick? Well, a convenient way of doing this is to just pick the unit tangent vector, right? Once you specify that you want it to be unit length, remember, unit vector is just a vector that has length 1, right? So a unit vector has length 1. So if we decide to pick tangent vector that has length 1, then there's only two options. There's the one that has length 1 that points in this direction, and then there's the one that has length 1 that points in the exact opposite direction, because they both lie on that tangent line. Okay, but the point is that you've nailed it down enough. And as far as the direction goes, well, we'll talk about that, like I said, at the end of, before I talk about curvature, we'll talk about this. Okay, and so I want to, whether you realized it or not, you were actually doing this in Calc 1. You just didn't frame it in terms of vectors, right? But now it makes more sense to talk about vectors. And so, going back to the definition that I wrote at the end of lecture last time, if I have a curve in space and it has a smooth parameterization r of t, of course, if that parameterization is smooth, one of the main things to remember about a smooth parameterization r is that r prime of t is never 0, or is never the 0 vector for any interior points, right? So if I toss away the endpoints, I don't have to worry about r prime of t ever being the 0 vector, and that's good because I'm dividing by the length of r prime of t here. An easy way to check, this is kind of an aside, right? And this is relevant to the homework that I assigned yesterday. Quick way to check if r prime of t is ever the 0 vector, right, for any t. What is a quick way to do that? compute the length. Why might this be a better thing to do than just looking at r prime of t, right? So if you compute r prime of t, that's some vector valued function. When you compute the length of that vector valued function, that is a real valued function, right? Or scalar valued function. Okay. And so, when you compute the length of this thing, you're moving it to the realm of being a real valued function. And so all you have to do is say whether or not this is, or figure out whether or not this thing can ever be 0 versus checking whether each component individually could be 0 simultaneously, right? This is typically, another reason that this is nice is because a lot of times you have to compute this anyway for the computations you're doing. And so this is a good idea to do this anyway. And so, of course, compute this and check whether the length of r prime of t is equal to 0 for any t. All right. If it is, then the curve in question is not smooth. All right. Now that's important because, as I said, our tangent vector is defined specifically in this way. So r prime of t divided by the length of r prime of t. So the reason why this particular form is chosen, of course, is, as I said last time, this guarantees that the tangent vector computed in this way is always unit length. So this goes back to that thing that I wrote on the previous page where I was saying we want to pick out a particular tangent vector. Okay. And so, what else is there to say here? This is how I compute my tangent vector. This is how I compute my normal vector. First question you might have is, why are these things perpendicular? First of all, what is the normal vector? You've heard of the tangent vector to a curve. You've heard of the normal vector to a plane, but what's a normal vector to a curve? Normal vector is just a particular choice of unit vector perpendicular to the tangent vector at a point. So here's a good example of what the normal vector looks like. Okay. And so the question is, why is n perpendicular to t? Why does this work? Okay. Well, this is the thing that I referred to a few lectures ago when I said that I was skipping a lot of the early chapter 12 stuff, but I would come back to one thing that we needed. Here's the one thing. So here's a fact that we had skipped over previously about vector valued functions that we need now to explain why these things are actually perpendicular. So if f of t is a vector valued function and the length of f of t is equal to a constant, and f prime of t exists wherever it needs to exist, but we'll say that it exists for all t. You can have a slightly more general statement here. It doesn't actually have to exist for all t, but I'm just going to make it easy for us and say that it does. Okay. Then, what is true? Well, then, if I compute f prime of t, and I dot that with f of t, what I get is 0 for all t. What does that mean? Well, when you dot two vectors together and you get 0, that means the vectors in question are perpendicular. So what it means is that f and f prime are perpendicular. Now, you might be confused by this. You might be confused by this because you might be thinking, wait. If I have a vector valued function f of t, and I'm thinking about that as tracing out a curve, right? Because that's our main use of vector valued functions. So I'm thinking about that as tracing out a curve. When I compute f prime of t, which is a thing I'm associating with being a tangent vector to my curve. Right? In fact, t is, if my vector value function is this parameterization function r of t, t is r prime of t, and yeah, I'm dividing by the length of r prime of t, but say that I have a really nice parameterization and this length is 1, right? So that my tangent vector is just r prime of t. Well, then you're saying that's tangent to r of t. So t is tangent to r of t. But this would say, in that case that I've mentioned here, that actually it's perpendicular to it. Can it be tangent and perpendicular? The answer is yes, and you'll see this in the case of a circle, why this isn't confusing, because this f of t you can think of as a position vector that's pointing out the position, right? So as this position vector is tracing out the position of the curve, position vector points this way, and the tangent vector is going to point perpendicular to it, okay, in this instance. Okay, that's the idea here. Okay. All right, and so how does this work? Actually, we can do a quick proof of this. All it relies on is some of those algebraic things we skipped over. So first of all, start with this statement that the length of f of t is a constant. Okay. Okay, but what's the length of a vector? What's another way of writing that? Well, the length of a vector, another way I could write that is I could write that as the square root of that vector dotted with itself. Right? This is the square root of f of t dotted with itself, and that's equal to a constant. That's what this says. This is just some trickery. Remember that you could think of the length of a vector coming from the dot product in this way. So it's square root of the vector dotted with itself. Okay. So here I can square both sides. And what I get is f of t dotted with itself is equal to whatever that constant is squared. Okay, so it's constant squared. I don't care what it is. It's still just some constant. Okay, and the reason why I don't care is at this step I'm going to take a derivative of both sides. So I'm going to take the derivative with respect to t of both sides. So ddt of that side and ddt of this side. So this is Calc 1 differentiation, right? I'm just taking derivative with respect to a single variable. So ddt of a dot product of two vector valued functions. How does that work? This is another one of those things that I skipped over because it's something that we don't have to do very often. We just use this fact. The way this works is that actually there is a product rule that works where the dot product plays the role of pointwise multiplication. So what happens here is that this is ddt of f of t dotted with f of t plus f of t dotted with ddt of f of t. So this is actually f prime of t dotted with f of t plus f of t dotted with f prime of t. So there's a product rule for the dot product of vector valued functions. What is ddt of constant squared? Well, it's 0. Right? It doesn't matter what it is. It's just constant, and so derivative of that's 0. But what do you notice about these two things? These are equal because the dot product's commutative. It doesn't matter what order you do the dot product in. So this tells me that 2 times f prime of t dotted with f of t is 0. But now I'm going to divide by 2 and get that f prime of t dotted with f of t is 0. And so that's why this works. Okay. All right. And so this doesn't just come out of nowhere. The reason for defining the normal vector in this way is because if you have vector here, you have vector valued function, and the main thing is you want to define a vector that is perpendicular to it at any point, and you knew that it has constant length. Well, the thing to do is to consider the vector t prime. Okay. Now we also want so t prime itself would be perpendicular to t, but it wouldn't be unit length, so we scale it by its length, and that's where both of these come from. Okay, so let's do a quick example of showing this, and again, You might get sick of it. I promise we're going to do more interesting examples soon. But first thing is to, you're really calibrating things here. So you want to check that it works on the simplest possible example. So consider the curve. What is Kirkle is what I was going to put here. So the curve C that is given by the parameterization, let's say a circle of radius r centered at the origin in the plane. So r cosine t I plus r sine t j. So t is from 0 to 2 pi. And we'll say that r is just some real number. Right? Well, it should be positive if it's going to be radius, so r is positive. Okay. And so, what does this look like? Even the axis is not straight. Okay. So that's bad circle, but here's r. This is what this thing looks like. We know this. So here's what my curve looks like. I want to actually compute the tangent vector using this formula to see that what I get makes sense, right? So the tangent vector using this formula is r prime of t over the length of r prime of t, okay? So let's see how this works. So I need to compute r prime and its length. Okay, so let's try to efficiently do this. So r prime of t is, little r is just a constant. So I have constant times cosine t. Derivative of that is minus r sine t I. Okay, derivative of r sine t is r cosine t, so this is plus r cosine t j. Okay. What do I mean when I say the length of f of t is constant? I mean that I don't mean that it's scalar. Of course it's scalar. I mean that it is constant with respect to t. So you plug in whatever value of t you want, and it's the same value. That's what I mean by it being constant. Okay. So I take the length of r prime of t. And what do I get? This is square root of minus r sine t squared plus r cosine t squared. So this is square root of r squared sine squared t plus r squared cosine squared t. So this is, I can factor an r squared out, so this is square root of r squared times sine squared t plus cosine squared t. What is that? This quantity is 1, of course, Pythagorean identity. So sine squared t plus cosine squared t is 1. So this is square root of r squared, or just r, right? This would be absolute value of r, but we know r is positive, so this is just r. And so t, this tangent vector, is r prime of t, that vector, divided by the length of r prime of t, which in this case is a constant. Okay, that is not always going to be the case. In fact, in general, this length is going to depend on t. Okay, we'll see a very, very simple example later where you think the curve in question is really simple, but actually computing the tangent normal vector is kind of annoying. Okay, and so I'm dividing by r here. So I take r prime t, I divide by r. What do I get? I get minus sine t I plus cosine t j. That's my tangent vector at r of t. So this is tangent to c at r of t. So any point that I want to discuss, I can find the tangent vector. Let's quickly compute the tangent vector at a few points here. So for instance, the tangent vector at t equals 0, that's r equals 0 or r equal 2 pi here. What is this thing going to be? So t of 0 is minus sine 0 I plus cosine 0 j. What is this? This is 0 I plus 1 j. What vector is that? Well, that's the vector 0, 1, so it points up here. All right, so that's t. This is t of 0. All right, let's compute t of, just to see what's happening here, let's compute t of pi over 2. So this is minus sine pi over 2i plus cosine pi over 2j, which is minus 1i plus 0j. So that's a vector minus 1, 0. There it is, right? So this is t of pi over 2. That's the tangent vector at r of pi over 2. Okay. Let's check t of, let's do, how about t of, we'll say, just to see what's going on here. Maybe we'll just try pi over 4. Yeah, you could try the others, of course. T of 3 pi over 2, it's going to look like that. But let's try t of pi over 4. So this is minus sine pi over 4i plus cosine pi over 4j. So this is minus root 2 over 2i plus root 2 over 2j. What does this look like? So at the point r of pi over 4, this looks like this. Now, a couple of things to note here. So one, note that I started with r, and so I started with this parameterization. Okay, I had no more info, just this parameterization what I started with. And when I computed this tangent vector, it is dictating a direction around the curve. Okay, this direction around the curve is known as the orientation of the curve. And so in this case, this would be my normal circle of radius r centered at the origin in the plane. And it's oriented counterclockwise. Okay. Now, could I have come up with a parameterization of this exact same curve where the orientation was different, right? Where it was oriented going clockwise? Yes, of course, I could. So the parameterization itself has baked into it the orientation. Okay. And so this is the idea. Someone said in chat, I thought t is something divided by r. Well, r prime has r in it, right? So when I divide by r, the r goes away. Right? That's what happens here. So r prime has the r in it, but I'm dividing by the length of r prime of t, which is just r. So the r goes away, and I'm left with minus sine t plus cosine t, which is what I get here. Okay. Okay. So that is the tangent vector. Let's do the normal vector for the same curve. Okay, so let's compute the normal vector. So the normal vector, as we recall, is the derivative of the tangent vector we found divided by its length. And so the process here is pretty straightforward in terms of what you do. Obviously, you got to compute the tangent vector first because you can't compute the normal vector without computing tangent vector first. Okay, and so let me just rewrite from last time. So t is minus sine t I plus cosine t j. Okay, so then t prime of t is going to be, so the derivative of minus sine t is minus cosine t I. Derivative of cosine t is minus sine t, so this is minus sine t j. Computing the length of this is going to be pretty quick. So the length of t prime, t is square root of minus cosine t squared plus minus sine t squared. Well, this is 1. Okay. And so actually, my normal vector is pretty easy to compute here. My normal vector is just t prime divided by 1, so it's just t prime. It's just minus cosine t I minus sine t j. Okay. So let's compute some of these normal vectors to make sure that they make sense on that same picture. I'll bring the picture back once we do. So let's do n of 0 here. So n of 0 is minus cosine 0 I minus sine 0 j. So that is minus 1 I minus or plus 0 j. Guess it doesn't matter. Okay. So let's put that on our circle here. So on our circle, what would this be? This would point in, right? Now, of course, if this were a circle of radius 1, it would point in all the way. It would touch here, but this is a circle of radius r. I just drew it like that. But this is, so it's not always going to point all the way in. It depends on the radius, so there's n of 0. Here, let's do n of pi over 2. So this is minus cosine pi over 2 I minus sine pi over 2 j. So this is 0 I minus 1 j. And again, it is exactly as you expect. It points in like this. All right. Okay, and if you compute at these points, you'll see that it points in like this. Okay. Now you might say, wouldn't it be perfectly fine if all you cared about were the geometric relationship of these vectors, meaning I just cared that the vector's tangent. So would it be okay if the tangent vectors and normal vectors I use here were flipped? Not for this parameterization. So when you're given a parameterization and you compute the tangent normal, then, I mean, that's just what you get for that parameterization. Now, what this means is if someone hands you a parameterization and just wants you to compute the things, then you have no choice. The only time there's a choice is when the orientation doesn't matter. Okay. On the other hand, someone could not hand you the parameterization. They could just say, consider this curve oriented counterclockwise, right? Well, then they're telling you the orientation, so they're dictating what the parameterization has to look like. Okay. So in general, you don't have to worry about orientation too much. This is exactly where it comes from. Okay, let's do the helix. Okay, so let's do the helix to see a slightly different example. Consider the helix as we saw before. So this is our helix in space. We'll say it's a cosine t I plus sine t j plus t k. All right, and t, we'll do a couple loops. Okay, of this helix. All right. If I wanted to compute the tangent vector here, well, tangent vector, again, it is nice to write this over and over again to ingrain it in your head that this is how it works. So I have to compute these two things, r prime and the length of r prime. So r prime of t, not too bad here. Again, this is minus sine t I plus cosine t j. Plus 1 k, yeah. And so the length of r prime of t, we actually computed this when we did the length, computed the length of this helix, right? So we did a similar thing because you have to compute this quantity when you're computing the length of the thing anyway. So if you have a multi-part question, right, that's asking you to compute the length of a curve and then later asking you to find the tangent normal vectors to it, you have to compute these quantities to find the length anyway, so you can be a lot more efficient, right, by just going ahead and computing these quantities. So the length of r prime of t is square root of minus sine t squared plus cosine t squared plus 1 squared. So this is square root of 2. Okay. And so what I get here is that t is r prime of t divided by square root of 2. So this is minus 1 over root 2 sine t I plus 1 over root 2 cosine tj plus 1 over root 2 k. Okay, so that's what my tangent vector is. Okay, so then what about my normal vector? So normal vector, again, this is t prime of t over the length of t prime of t. Okay, and this, well, I'll compute these separately. So t prime is what? So this is minus 1 over root 2 cosine t I plus 1 over root 2 sine t j plus 0 k, right? Derivative of 1 over root 2 with respect to t is just 0 because it's constant. And so the length of t prime of t is square root of 0 squared is not going to contribute anything. So this is minus 1 over root 2 cosine t squared plus 1 over root 2 sine t squared. So what is that? This is square root of, when I square these things, I get 1 half cosine t plus 1 half sine t. So I get 1 over 2 times cosine squared t plus sine squared t. All right. And so I get 1 over root 2. So this is 1 over root 2. Okay, and I'm dividing by that, of course, here. So this is the same thing as root 2 times t prime. And so n is minus cosine t I plus sine t j plus 0 k. What do I need? Negative. It's possible. Let's see. Where do I need negative? Oh, here. Yeah, I do. It should be a negative. Yep. So now it's right. Yeah, that should be negative. Okay. Now, both of those examples are fine. These are good. Now you've computed tangent normal vectors for circle and plane and a circular helix in space. The thing I'm going to warn you about, though, is that these calculations get extremely complicated very quickly, even for curves that are seemingly really, really simple. And so the thing that I always get, of course, this is, usually it's more of a concern when we're in person because there's time concerns. But it's a concern for you all too. The question is how simplified do I need to get here? Right? Now for these, of course, these lengths that we were computing were constant, so it was all nice. But typically they're not going to be, okay? So the question is how simple do I need to make these? And my answer to students is always this. You don't have to worry about making it too simple if you're not going to do any calculations with it. So the normal vector can look nasty because you're done when you get there. Okay? But your tangent vector should be as simple as possible. Okay? And this isn't for me to grade you. It's not for me and the TAs to be able to grade your exam, although it helps. It is specifically because you are going to be computing with these quantities. And there are some instances where if you do not simplify, it is basically impossible for you to do the computations. Okay, so if you don't notice some simplification, some of these computations are completely impossible because it would have you expanding some really, really horrible thing. So let me show you how bad it can get with even just a very, very simple curve. So here's some practice. So example, parameterize the curve y equals x squared in the plane and find its tangent and normal vectors at any point. Okay. So I want to parameterize the curve y equals x squared in the xy plane, and I want to find its tangent and normal vectors at any point. Okay, so I know what this curve looks like. Right here it is. Maybe it's a little too flat, but that's how it looks. Now there's a trick, right? There's a trick because there was a trick. The same trick existed in Calc 2. When you have a curve that is very simple, and here very simple means it's the graph of a function, right? So you have a function, f of x is x squared, and when you have the graph of a function, it's really easy to parameterize it, right? It's just xi plus f of xj, right? Like that's the parameterization. Okay. So in this case, my curve C is parameterized by r of t, where this is ti plus t squared j. Right? It's just t f of t, but the function is just x squared. So I'm just plugging in the parameter. Okay. So this is it, right? Where t is just some real number. Okay, so very simple parameterization here. All right, so there's my parameterization of y equals x squared. Okay. So then what do I do? Let's compute tangent vector, right? T of t is r prime of t over the length of r of t, or r prime of t, sorry. Okay, so I need to compute these two quantities like always. So r prime of t is 1i plus 2tj. Okay, off to good start. All right, so then length of r prime of t is square root of 1 squared plus 2t squared, which is square root of 1 plus 4t squared. And you might be like, well, that's not too bad. But then you remember what you actually have to do with this thing, right? And then you start to be concerned, right? And so the tangent vector for this parabola is r prime of t divided by the length of r prime of t. So this is 1 over the square root of 1 plus 4t squared I plus 2t over the root of 1 plus 4t squared j. Okay, so there's my tangent vector. Oh no, right? This is suddenly not looking too good. Okay, so that's just the tangent vector for this very, very simple curve. Right? It doesn't get more simple than this. Right? Yet the tangent vector is this thing. Okay. All right. Where did the 1 and the 2 come from? Well, I took the derivative of r of t. So derivative of t is 1, and derivative of t squared is 2t. Right? So that's where the 1 and the 2t come from. Okay. So now I have to compute the normal vector. But the normal vector is, again, t prime over the length of t prime. Ooh, this is not looking too good. How do I find r of t? So this is the trick of when I have a, maybe I'll do an aside here. So aside, if c is a graph of a function, all right, so y equals f of x, then a parameterization, so this is in the plane, then a parameterization of c is r of t, which is ti plus f of t j. And t is in the domain of the function, where d is the domain of the function. Okay. So this is a trick that you used in Calc 2 and I mean, this is not just a trick, this is the great thing about parametric function and parametric curves, is that it's more general than what you did before. So literally everything you did from high school, right, from middle school until, Calc 2, all that stuff could have been done parametrically. because parametric curves are more general than the normal curves you were dealing with that whole time. Okay, and so when you have a curve that's just a graph of a function, it's just t f of t. So in this case, our function was x squared, so it's t squared. Okay. So anyway, now going back here, I have my tangent vector t. This is I have to take the derivative of this, right? So it's going to get ugly because I'm going to have to use a bunch of quotient rules. So I have to compute t prime, and then I have to compute the length of that. So let's do that. Okay, so what is t prime of t? So let's remind myself what t of t is. Let me fold paper real quick. So there's t. Okay, so now I'm taking the derivative. So I'm taking the derivative in each slot here. So it can help to do this. You know, you can use exponents if you want to use exponents. You could do that. So this is if you like, you can write this as 1 plus 4t squared to the right. So here, let's rewrite t here, and then let's compute the derivative. So rewriting t, I'm going to rewrite t as 1 plus 4t squared to the minus 1/2 I plus 2t times 1 plus 4t squared to the minus 1/2 j. Okay. Now you don't have to do it this way. You could do it with the quotient rule using the keeping them in the denominator, but I'm going to do it like this. So if we do this, then what do we get when we compute t prime? So t prime is minus 1/2 times 1 plus 4t squared to the minus 1/2 minus 1, so this is minus 3/2 times the derivative of what's inside. So this is power rule and chain rule, right? So chain rule says that this would be derivative of what's inside, which is derivative of 1 plus 4t squared. So that's 2 times 4t, so that's 8t. All right, I. Okay, plus, a product rule here. Now, you can do it as a product rule, or you can do it as a quotient rule. It doesn't matter. I'm going to do it as a product rule here just for extra Calc 1 practice. So doing it as product rule, what is this? This is, better put a bracket here. This is 2 times 1 plus 4t squared to the minus 1/2 plus 2t, let's give myself more room here, plus 2t times 1 plus 4t squared to the minus 3/2 times 8t. And all that's times j. Okay. So what is this? So let's simplify this a little bit. So this is going to be minus 4t times 1 plus 4t squared to the minus 3/2 I plus some ugly quantity here. And in order to make this work, what I am going to do is I'm going to straight up rewrite this, and then I'm going to show you what to do here. So this is 2 times 1 plus 4t squared to, I'm just rewriting this. I'm not doing anything else. Well, I'll combine these two. Plus 16. There should be an extra 1/2 here. So there should be an extra, minus 1/2 here. Yeah, when I computed this derivative, this should be there should be a minus 1/2 here somewhere. I'll put it here. Okay, so then this is so this is minus 8t squared. 1 plus 4t squared to the minus 3/2 j. Okay. Yeah. Okay. All right. So this term is as good as it's going to get right now. So this is minus 4t times 1 plus 4t squared to the minus 3/2 I. Here I'm going to factor out 1 plus 4t squared to the minus 1/2. Okay, so I'm going to factor that out. So this is going to be plus 1 plus 4t squared to the minus 1/2 gets factored. What gets left behind? Here, this is just going to be 2. Here, I have minus 8t squared. And when I factor out 1 plus 4t squared to the minus 1/2, right, what is happening, right? What am I doing when I do that? Okay. Well, factoring out by pulling out a 1 plus 4t squared to the minus 1/2, it multiplies this thing, right, by 1 plus 4t squared to the 1/2, right? And so this is actually 8t squared times 1 plus 4t. Do I want to do this? So this is actually to the minus 1 j. Do I want to leave it like this before I compute the length? I believe there's an easier. Oh, no. Actually, no. This is not what I want to do. I want to. Yeah. No. This is bad. So let's not do this. I factored out the wrong thing. That's no good because this is a minus 1. I want a positive 1 to be there. So this is minus 4t times 1 plus 4t squared to the minus 3/2 I plus what I'm going to factor out here actually is 1 plus 4t squared to the minus 3/2. So 1 plus 4t squared to the minus 3/2 gets factored out. Now that might look horrible at first. What happens? When I factor out by 1 plus 4t squared to the minus 3/2, that's the same thing as multiplying by 1 plus 4t squared to the 3/2 here. And so what is left is this is 2 times 1 plus 4t squared to the first minus 8t squared, right, times j. There we go. Okay, now this is nice because 2 plus 1 plus 4t squared, I'm going to distribute that and the 8t squared cancels out. And so what I have left here is minus 4t over the square root of, or I'll just leave it as 1 plus 4t squared to the 3/2 I, right, plus what happens here is I get, just working this out, this is 2 plus 8t squared minus 8t squared, those cancel, and what I'm left with is plus 2 over 1 plus 4t squared to the 3/2 j. Right? Okay. This is t prime, right? So I have to compute the length of this. So no reason to stop now. So what is the length? So this is t prime. This is t prime of t. So what's the length of t prime of t? So the length of t prime of t is, it's not as horrible as you think it's going to be. You're like, oh my god, that is awful. It's not so bad. So minus 4t over 1 plus 4t squared to the 3/2 all squared plus 2 over 1 plus 4t squared to the 3/2 all squared. What is that? Well, this is square root of the top is minus 4t times minus 4t, so that's 16t squared over, well, squaring this is easy. That's 1 plus 4t squared all cubed plus 4 over 1 plus 4t squared cubed. Okay, I promise this story has a moral. There's a moral to this tale. All right, so this is equal to square root of, I can combine these. These have the same denominator. I can add them together, and I can actually factor out a 4. And when I do that, I get 4 times 1 plus 4t squared. Oh, would you look at that? Over 1 plus 4t squared cubed. One of these cancels, leaves me with 2. Oh, that has an easy square root. That's 2 over 1 plus 4t squared. So that's not too bad at all, right? Sorry, over the square root of 1 plus 4t squared. Yeah. No, I had it right. Because this is squared here. Yeah, sorry. Okay. All right. So, going back, what is the normal vector? The normal vector in is t prime divided by the length of t prime, which is this. Okay. And what is that normal vector? Well, dividing by the length is multiplying by this reciprocal. And so what do I get here? So this is actually pretty easy to compute, multiplying this out. I have 1 plus 4t squared now in the numerator. That is going to leave a 1/2 in the denominator. So this is, and there's going to be a 2 here. So this is minus 2t over the square root of 1 plus 4t squared I plus 1 over the square root of 1 plus 4t squared j. Now, here is a couple of things to say about this. So one, let's not lose sight of what we're doing. What is it that we're actually doing? We're finding the tangent and normal vector for this curve, right? Okay, so again, this drives home that even for a curve like this, doing this computation can be involved. Another thing, would you have had any hope of computing the length of t prime and thus the normal vector if you had not simplified this, right? If you had left this in some expanded form like this, do you have any do you have any hope that you could have computed the length of t prime if you had left it in a form like this? Well, no, right? It would be really hard to do it that way. Okay. So that's one thing to say. The other thing to say is why would this very simple curve have a normal vector that is so awful, right? Or seemingly awful? Well, think about what the normal vector is for this curve. So the tangent vectors are easy to see, right? And if you actually compute them, I've run out of time so I can't, but if you actually compute them, then this is what they look like. This is what the tangent vector looks like at all those points. But look what the normal vector is having to do. Here it is. You can actually compute. So if you compute n of 0, what do you get? 0, 1. So you get 0, 1 as a vector, right? Which is exactly what you expect. But look what the normal vector has to do here, right? It has to look like this. Right? These are weird vectors. So it's not that surprising that the description of those vectors would be something kind of complicated. Right? Okay. So the main reason I did that was so that you can see what you should do is to make your tangent vector as simple as possible. Make t prime as simple as possible. Once you've computed the length of t prime, it's not that big of a deal. Because, in fact, in most cases, you don't even necessarily need to rewrite the normal vector as something decent. You can just literally say normal vector is t prime divided by the length of t prime. So if it's some long thing, that's good enough. But you do have to compute the length of t prime. And if you don't want to torture yourself, that means that t prime itself should be as simple as you can possibly make it. Okay. Do the normal vectors always tend to face inwards? So the question is, this is a chicken and egg situation. The question is, or is it that the orientation we consider to usually be the positive one is the one that has the normals facing inwards? So basically this depends on the orientation. And so if you lived in a world where your orientation of a circle was always clockwise, right, then this changes what's going on here. Okay, so basically inside and outside, and that is it It's a good question because even though it's a simple question, it is actually really hard to discuss some of these things because in the case of curves, it's easy enough to visualize, but later we're going to talk about tangent planes to surfaces and normals in that sense, and these questions of orientation become really, really confusing very quickly. Okay, so the answer is that for most of the standard oriented curves that we're going to talk about, the normal is going to face inward, but what determines inward versus outward for some of these curves, right? All right, if it's closed, then maybe you can tell me what's inside and what's outside, but if it's not, then what's inside, what's outside, right? Anyway, so that's it for today. On Wednesday, we'll talk about curvature, and I'll do a bunch more examples of curves. I'll do some really cool curves on Wednesday, so I promise the curves will be more exciting. And then Friday, I'll do more of this stuff, basically tidy up everything from chapter 11 and 12, and I'll post your exam on Friday. So anyway, I will see you all on Wednesday.